In this video, we're going to try to understand areas of parallelograms in the plane, volumes of parallelepipeds in three-dimensional space, and what these things have to do with determinants. So we start with areas in the plane. So let's suppose that we've got two vectors, A and B, and A has components A1 and A2, so it's A1I plus A2J, and likewise B is B1I plus B2J. And we want to figure out what the area of this parallelepiped is. Now, we know what it is geometrically, because if we call this angle theta, and we sort of drop the perpendicular, then the area should be the length of A times the length of B times the sine of this angle. I guess we're doing lengths with... Okay, but how do you figure out the sine of the angle? Okay, we're going to go a different route. In the end, it will equal AB sine theta, but we're going to get it a different way. Okay, the first things we notice about the area is it's a signed area. It's actually going to give us a negative number. Our formula is going to give us a negative number sometimes. It's either going to give us the area or minus the area. The second is that it should scale right. And then we have that it should scale right. If you multiply A by 2, if you make A twice as long, you get twice as much area. If you make B twice as long, you get twice as much area. Either way, you get twice the area of the original. And this is why we see it has to be a signed area, because if lambda is negative, then suddenly you get a negative answer. And it should add, if you take a sum of two vectors on the right-hand side, it should be what happens if you get the first vector plus what happens if you get the second vector. And the same thing for the first side. If you pick any vector twice, the answer should be 0. And here's the biggie. If you switch the order of the vectors, you switch the sign of the answer. This isn't like regular multiplication where 3 times 5 is the same thing as 5 times 3. If you take B and then A, you get minus what you had if you had A and then B. So let's take a look at why this is true. For the additivity, suppose you have A and B. That gives us the area of this rectangle. If you had A and C, it would give you the area of this rectangle. If you put them together, you get the area of this rectangle plus this triangle minus this triangle. Those two triangles are congruent. They have the same areas. So this area plus this area is the same as this area. So what happens when you put in B plus what happens when you put in C gives you what happens when you put in B plus C. And likewise scaling. If you make A twice as big, you get twice as much area. You make B twice as big, you get twice as much area. And if you put the same vector twice, you would have A, and your whole parallelogram would be squashed. It would be one-dimensional. You'd have no area at all. So now let's take a look at what happens if you put in A plus B twice. You FOIL it, the first, last, first, outside, inside, and last. And you see that this term has to be 0 because it's A twice. And this term has to be 0 because it's B twice. And this term is 0 because it's A plus B twice. And so whatever AB gives you is minus what BA gives you because they add up to 0. In other words, if you get it BA, you get minus what you would have from AB. So now we can apply this to our standard coordinate vectors. If you feed it I twice, you got to get 0. If I feed it I and then J, well, that just gives you the unit square. So that has an area of 1. But that means that if you feed it J and then I, you have to get negative 1. And J and then J, you have to get 0. So now we're ready to figure out the grand formula. We just take any two vectors A and B, expand them in terms of I and J, and FOIL it. The first term is 0 because that's I twice. The last term is 0 because that's J twice. This term gives you A1, B2. And this term gives you minus A2, B1 because A of Ji is minus 1. You put it all together and you get A1, B2 minus A2, B1. And that is a determinant. It's the determinant of the 2 by 2 matrix A1, A2, B1, B2. So areas are given by determinants. And in general, the way that you compute a 2 by 2 determinant is you just take the cross terms. You take AD with a plus and BC with a minus. The terms that go down and to the right go plus, down and to the left go minus. It's a crisscross, AD minus BC. So that's it for areas. Now we're going to move on to volumes. So we're going to play the same game as we did before. Now we're in three-dimensional space, and we've got three vectors, and we want to figure out the volume. And we're not going to go through the whole derivation all over again, because it's really the same kind of arguments that we did for area. We've got this quantity V of A, B, and C, and it's going to give us our signed volume. It's going to give you the volume of this parallelepiped if you have a right-handed system. That is, if when you take your hand and you start off with A and you rotate to B, then your thumb is pointing in the C direction. And it's going to give you minus the volume if you have a left-handed system. And if any two vectors are the same, then the parallelepiped collapses to two dimensions, and you get nothing. And if you swap any two vectors, you flip the sign. And so now we can look at our basis vectors. If I give you ijk, that just gives you the unit cube. And jki gives you the same thing, because you get this by swapping things twice. If you swap the I and the j, and then you swap the I and the k, you get jki. And likewise, you get kij. And the way to remember it is this is a cycle. ijk, 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 ijk. As long as they keep going in that cyclic order, ijk, ijk, jk, ij, you get a plus 1. And if they go in the opposite order, if they go jik or kji or ikj, you get a minus 1. So now, when we write out our volume, now there are three terms here, there are three terms here, there are three terms here. You put it all together, they're going to be 27 terms, but all but 6 of them are 0. The only 6 terms that you get are when you have one I, one j, and one k. And that's called the 3 by 3 determinant, the determinant of the 3 by 3 matrix A1, A2, A2, 3, B1, B2, B2, 3, C1, C2, C3. Now the way that you compute a 3 by 3 determinant is you're going to take these products, and I'm going to write it, I'm going to copy over a couple of the terms, because the terms we want is we want A1, B2, C3. And we want A2, B3, C1 wraps around, but it's easier to write it with the extra copy. So these terms are positive. A1, B2, C3, A2, B3, C1, A3, B1, C2. And these terms are negative. Those are the 6 terms that contribute. Now another way to compute this is you could look at what is, it's A1 times B2C3 minus B3C2. In other words, it's A1 times a 2 by 2 determinant and minus A2 times a 2 by 2 determinant plus A3 times a 2 by 2 determinant. So to finish this off, let's work an example. Let's compute the determinant of this matrix. Okay. Using the first method, we copy over the matrix and we copy over the first 2 columns. And then we look at our diagonals. 1 times 1 times 2, negative 1 times 3 times 1, 1 times 2 times 4. Those are the plus terms. Then we subtract 1 times 1 times 1. We subtract 1 times 3 times 4. We subtract negative 1 times 2 times 2. And that gives us 2 minus 3 plus 8 minus 1 minus 12 plus 4, and it's negative 2. If we did it the other way, we would have gotten 1 times this 2 by 2 block, and then minus negative 1 times this 2 by 2 block, plus 1 times this 2 by 2 block, and it gives you the same answer. In fact, it gives you the same terms. You wind up with the 2 minus 12, that's the 2, and that's the minus 12. 4 minus 3, 8 minus 1. It gives you exactly the same terms, exactly the same answer.